We were told the Norden bombsight won the air war. German engineers knew that was a lie, and they scoffed at the very heart of the American design. German pilots looked at America's most secret weapon, the gyroscopic bombsight, and they weren't impressed. They knew a secret about aerial warfare we were forced to learn the hard way. America bet the lives of tens of thousands of airmen on a single piece of technology. But in German cockpits, they knew its fatal flaw, and they called it a failure. In the stories many of us grew up with, the Second World War in the air was a story of American muscle and American ingenuity. It was a sky filled with B-17s, the flying fortresses, thousands of them, blotting out the sun on their way to Germany. And at the very heart of that fortress, inside the plexiglass nose, was a secret weapon, a device so prized, so valuable, that bombardiers were ordered to guard it with their lives. This was the Norden M-series bombsight. It was more than a legend. It was a promise. A mechanical computer that, the newspapers and newsreels told us, could drop a bomb into a pickle barrel from 20,000 feet. We believed this was our ace in the hole. This was the tool that would allow us to fight a different kind of war. Not the brutal, muddy slaughter of the trenches, but a clean, surgical war. We would destroy the enemy's ability to fight, one factory, one railroad, one bridge at a time. We believed in this promise, and we bet the entire strategic air campaign and the lives of tens of thousands of young airmen on this one single piece of technology. But across the English Channel, a very different story was unfolding. In the design offices of the Carl Zeiss Company and in the cockpits of Heinkels and Junkers, German engineers and bombardiers looked at our prized invention and they scoffed. This wasn't just national pride. It was a cold technical assessment. They weren't just unimpressed. They were, in their professional opinions, dismissive. They believed their own solution, the Lotfernrohr 7, or Lotfest 7 as it was known, was not just a match for the Norden, but was fundamentally and philosophically superior. How could this possibly be? How could they laugh at the very technology we were told was war-winning? The answer, as the title of this video suggests, is a fascinating and complex technical debate. It's a story about stabilizers, about gyroscopes, and about two completely different philosophies of how to fight a war in the air. The German confidence, that scoffing, reveals a truth about the air war and about the Norden itself that was kept very quiet for a very long time. The question we're setting out to answer is this: why did Germans scoff at American bombsights sans gyro stabilizers? Now that title, which we chose very carefully, holds the first and most important clue. And it also holds perhaps the first great misconception of the air war. Because the truth is, the American Norden was defined by its gyroscopes. It was a marvel of stabilization. It was, at the time, one of the most complex gyroscopic instruments ever mass-produced. So the premise that our sights were sans gyros or without them is the first myth we have to bust. The Germans weren't scoffing because we lacked gyros. They were scoffing because of how we used them. They were scoffing at our reliance on them. They believed our entire solution was a dead end. They saw it as a complex, delicate, and ultimately flawed approach to solving what was, without a question, the most difficult physics problem of the 1940s. And to truly understand why they felt this way, we have to go all the way back to the beginning. Before we can compare the machines, we have to respect the problem. We have to understand in detail what a bombsight actually does. Dropping a bomb from an airplane is not like dropping a rock from a bridge. It sounds simple, but it's a nightmare of physics. If you are in an aircraft, let's say a B-17 moving at 200 miles an hour, and you are 3 miles up, you don't drop the bomb when you are over the target. If you did, the bomb would land miles away. Why? Because the bomb, when it leaves the bomb bay, is not stationary. It retains all the forward momentum of the airplane that was carrying it. So from the very second it's released, that bomb is traveling forward at 200 miles an hour while it is also falling toward the Earth. Its path isn't straight down. It's a long, graceful, and predictable curve. That curve is called a ballistic parabola. The job of a bombsight, its entire purpose, is to calculate the exact release point on that curve. It has to figure out
How many seconds or how many miles before the target must I let go so that the bomb arcs perfectly onto the aiming point?
To do this, the bombsight needs to know, well, it needs to know everything. It's a computer that needs data. First, it needs to know your exact altitude. Not what the altimeter in the cockpit says, but your true altitude above the target. Second, it needs to know your exact speed. Not your airspeed, which is just how fast you're moving through the air, but your ground speed, how fast you are moving across the surface of the Earth. These are two very different things. And the reason they're different brings us to the third and most difficult variable, the wind. The wind is the eternal enemy of the bombardier. A crosswind at 20,000 feet could be blowing in a totally different direction than the wind at 10,000 feet. These winds push the bomb as it falls, drifting it hundreds, even thousands of yards off its intended path. The bombsight has to calculate all of this. It has to know the trail of the bomb, how far it will travel forward, and the drift, how far the wind will push it sideways. This is the bombing problem. It's a massive, multivariable equation that has to be solved in real time in a vibrating, freezing cold cockpit while people are actively trying to kill you. In the First World War, this was, as you can imagine, mostly just educated guesswork. Pilots were flying low, maybe a few thousand feet, and slow. Their sights were primitive. We're talking about a few nails hammered into the side of the cockpit or a simple grid of lines painted on the floor. The pilot would look down, line the target up with one of the nails, and pull a lever. It was crude, it was terribly inaccurate, but for the targets of that war, a trench line, a bridge, a railroad yard, it was just good enough to be terrifying. But after that war, the great theorists of air power, men like WWII in Italy, Hugh Trenchard in Britain, and our own General Billy Mitchell, they weren't dreaming of harassing trenches. They were dreaming of something much bigger. They were dreaming of strategic destruction. They built an entire doctrine, a new theory of warfare that said air power alone could win the next war. They believed that fleets of bombers flying deep into enemy territory could destroy a nation's factories, their oil refineries, their power plants, and their entire will to fight. They argued you could win a war without a single soldier ever having to cross a border. This was the birth of the strategic bombing doctrine, and this doctrine, this dream, created an impossible technical demand. It demanded that you must be able to hit a specific building, a single factory from 4 or 5 miles up, while flying through clouds and turbulence and enemy fire. The old nail in the side of the cockpit solution was now useless. You didn't just need a sight, you needed a miracle. You needed a computer. And so, America built one. It was designed by a brilliant, if famously cantankerous, Dutch engineer named Carl Norden. Norden had emigrated to the United States, and working in close cooperation with the U.S. Navy, he dedicated his life to solving the bombing problem. The result, after years of refinement, was the Norden Mark 15, known to history as the Norden M series. This was our answer. And we must be clear, make no mistake, this device was a mechanical marvel. It was, for its time, one of the most sophisticated analog computers on Earth. The legend of it dropping a bomb in a pickle barrel wasn't just propaganda, at least not at first. It came directly from a 1931 test report where a bombsight, under perfect conditions, in the clear skies of a test range, performed beautifully. The Norden was a dense, heavy block of metal, gears, dials, and wheels. The bombardier would lie in his stomach in the very nose of the bomber and look through a powerful telescope. He would input the data he knew, the altitude, the airspeed, the estimated wind direction and speed, the type of bomb. The sight's internal gears would begin to whir, calculating the basic ballistic curve. But the real magic, the part that cost as much as a new car and was guarded by armed sentries, was the stabilization system. Inside the Norden was a complex heart of spinning gyroscopes. A gyroscope, as many of us might know from our own kids' toys or perhaps from naval navigation equipment, is a spinning wheel or rotor. And thanks to physics, that spinning wheel wants to stay fixed in its orientation. No matter how you tilt or move the casing around it, the spinning wheel inside stays perfectly, stubbornly level.
The Norden used this principle to create what engineers call a stable vertical. It meant that as the B-17 bucked and vibrated in the turbulence, even as flak shells rocked the aircraft, the bombsight's telescope, the bombardier's eye, stayed locked onto the ground. It was perfectly level with the true horizon. It gave the bombardier a steady, stable platform to find and track his target. This alone was a revolutionary achievement. But it did something even more incredible. And this is the part that defined the entire American bombing philosophy. The Norden didn't just stabilize the sight. It stabilized the airplane. The bombsight was directly, mechanically connected to the aircraft's autopilot, specifically the C-1 autopilot. For the final critical moments of the bomb run, the bombardier was no longer just an observer. He was the pilot. He would find the target in his telescope and lock it in. From that moment on, he would use two delicate knobs on the bombsight itself to keep the crosshairs perfectly centered on that target. As he turned those knobs, the bombsight sent signals to the autopilot, which moved the aircraft's rudder and ailerons. The bombsight was flying the plane. In the cockpit, the pilot would just sit there, hands and feet off the controls, calling out over the intercom, "Okay, bomber, she's all yours." This was the American solution. Remove the fallible, clumsy, nervous human pilot from the equation. Let a perfectly stable, ice-cold machine fly the final critical 20 or 30 seconds. It was a beautiful theory. It was genius. It was revolutionary. And in the crucible of combat, it was, quite often, a terrible, terrible idea.
This is where the German Scoffed truly begins. Because the German engineers at the firm of Carl Zeiss, a name many of us will still recognize today from high-end cameras, microscopes, and binoculars, had faced the exact same set of physical problems. They also needed to stabilize the view. They also needed to compute the ballistic curve. Their answer was the Lotfern 7, or Lotfest 7. At first glance, the Lotfest 7 looked simpler, almost cruder than the Norden. It was a more compact, vertical periscope-style sight, rather than the Norden's bulky horizontal telescope. But it was built on a completely different philosophy. A philosophy born from a different kind of air force. The Germans looked at the Norden's core idea of the bombsight flying the plane, and they thought it was absolute madness. Why? Why would that be mad? Because in a combat environment, you are not flying in a straight level line, enjoying the view. You're being hunted. You're in what the crews called a flak alley, with hundreds of anti-aircraft guns on the ground, all calibrated to your altitude, filling the air around you with black puffs of smoke and flying metal. You have Messerschmitt 109s and Focke-Wulf 190s diving at you, their cannons winking as they fired. In that environment, the last thing a pilot wants to do is give up control of his aircraft to a machine that cares about nothing except flying in a straight line. The pilot needs to be able to jink. He needs to make small, constant, erratic movements. A little slip to the side, a small dip, a slight climb. These tiny, unpredictable moves were all that stood between him and a flak shell. It was the only way to throw off the enemy gunner's aim on the ground. The Norden's autopilot connection, the very heart of its design, demanded the exact opposite. It required 20 to 30 seconds, sometimes even a full minute, of perfectly straight, perfectly level, perfectly predictable flight. In the skies over Germany, this was called suicide. It turned the bomber into a perfect, non-maneuvering target for the master gunners of the Luftwaffe. The Germans knew this. Their flak gunners counted on it. So the Germans at Zeiss designed their system differently. The Lotfest 7 also had gyroscopes. This is a critical fact. But they served one purpose and one purpose only: to stabilize the bombsight's internal mirror, not the aircraft. Here is the genius of the Lotfest 7. The German bombardier looked through his eyepiece, and what he saw was a perfectly stable, rock-solid image of the ground below, even as the pilot was actively maneuvering the plane to avoid getting shot down.
The gyros created a stable view, decoupling the man's eye from the vibrating, jinking aircraft. The bombsight computed the release point, but it did not ever fly the plane. Instead, it fed information to the pilot. It had a device called the pilot direction indicator, which was a simple needle on the dashboard. The bombardier would track the target, and the sight would tell the pilot what to do. The needle would move left or right, and the pilot's job was simple: keep the needle in the center. The pilot retained full, precise control. He could follow the bombsight's gentle instructions for the aiming path while still making those life-saving jinks and adjustments. It was a partnership between man and machine, not a surrender to it. But, you might be thinking, that sounds less accurate. Surely the Norden's perfect machine-controlled straight-line run was more accurate in the end. That was the theory. That was the pickle barrel promise. But the reality of war in the skies over Europe was nothing like the clear, calm skies of the Nevada test range. The first and most devastating problem, the one that crippled the entire American precision bombing doctrine, was the weather. The Norden was a visual bombsight. The bombardier had to see the target. He had to physically put the crosshairs on the factory roof. But for most of the war, Northern Europe was covered in what the crews called solid overcast. It was a thick, impenetrable carpet of clouds that made visual bombing completely, utterly impossible. On mission after mission, the B-17s and B-24s would fly all the way to Germany, fighting through flak and fighters for hours, only to arrive at the target and find it completely obscured. They would be forced to turn around and fly all the way home with their full bomb load still in the bay, having never even seen their objective. This was the Norden's first and greatest failure. It was a precision instrument designed for a type of war that, in Europe, rarely existed. The Germans, on the other hand, had designed a system that was simply more rugged and more practical for the war they were fighting. The Lotfernrohr 7 was mechanically simpler than the Norden. The Norden, as we'll see, was a delicate, hand-built nightmare of thousands of moving parts. It was so sensitive to temperature and vibration that it had to be removed from the aircraft after every single mission by a specialist, placed in a padded, heated case, and stored in an air-conditioned, temperature-controlled vault. If it got too cold on the flight line, the special lubricants inside would gum up. If it got jostled too hard by a rough landing, the gyros would be thrown out of alignment. Maintenance was a full-time job for highly trained, elite specialists. The Lotfernrohr 7 was a piece of field equipment. It was built by Zeiss to be tough. It could be serviced in the field by regular aircraft mechanics, and it generally stayed in the aircraft mission after mission. It just worked. Now, here's a part of the story that sounds like it came straight out of a Hollywood spy thriller, but it is the absolute documented truth. The Germans didn't just suspect the Norden was flawed. They didn't just guess. They knew.
They had the plans. In 1938, a full year before the war in Europe even began, a German-born American citizen named Hermann Lang, a disgruntled man who worked at the Norden factory in New York, passed a complete set of blueprints for the Norden bombsight to the Abwehr, German military intelligence. For some of what was likely only a few $1,000s, he handed over America's most treasured military secret. The Germans took these plans back to the Zeiss factory. They built their own copies of the Norden. Their best engineers, including the legendary Dr. Max Schuler, the father of gyroscopic navigation, took it apart, studied it, and tested it. And after all that, they still preferred their own Lotfernrohr 7. They saw the incredible complexity. They saw the reliance on the autopilot. They saw the sensitive air-driven gyros. And they made the cold, calculated decision that their own system was better suited for the realities of aerial combat. So for the entire war, while we were guarding the Norden with pistols and swearing bombardiers to secrecy, the Germans had the plans sitting in a file cabinet. They had already reverse-engineered it, tested it, and decided no thank you. That is the source of the scoff. It was not the arrogance of ignorance.
It was the deep, technical confidence of an engineer who has seen his competitor's product, tested it himself, and knows, beyond a shadow of a doubt, that he has the better design. This all sounds like a terrible indictment of American technology. It sounds like we wasted billions of dollars, billions in 1940s money, and risked thousands of lives on a failed idea. And in some ways, that is tragically true. The dream of pickle barrel bombing in 10-ship formations flying through flak was a fantasy. After the war, the U.S. Strategic Bombing Survey, a massive, sober-eyed investigation, delivered the final verdict. It found that even in 1944, at the peak of our power with massive formations and total air superiority with our P-51 escorts, only about 50% of all bombs dropped by the 8th Air Force landed within a mile of their aiming point. Let that sink in. Not a pickle barrel, a mile. The Norden was not a precision weapon in practice. It was an area weapon. But, and this is a very important but, it was the best we had. The Norden's failure was a failure of doctrine, not entirely of technology. The idea that we could win the war with precision daylight bombing was the flaw. When the weather was clear, which was rare, and when the crews were experienced and not being shot to pieces, the Norden was incredibly accurate. It was far, far better than any level bombsight the British were using at the time for their mass formation raids. And here's another fact that is often lost to history, drowned out by the legend of the Norden. The Norden wasn't even our only bombsight. Because the Norden was so famously complex and so agonizingly slow to manufacture, the U.S. Army Air Corps was desperate for a backup. They invested heavily in a competing design, the Sperry S-1. Sperry, another American company name that is synonymous with gyroscopes, also built a gyroscopically stabilized sight. It was also connected to an autopilot. In many ways, it was a parallel design, born from the same strategic doctrine. But the Sperry had crucial differences. It used a different kind of analog computer, what's called a ball disk integrator, and most notably, it used electrical gyros, which were seen by many as more reliable and faster to spin up than the Norden's air-driven gyros. Many crews, especially those flying the B-24 Liberator, were equipped with the Sperry. And many of those bombardiers, if you read their memoirs, actually preferred the Sperry. They found it simpler to operate, faster to set up, and more robust in the field. But the Norden had better political connections, especially with the Navy, which had funded its initial development. The Norden won the production and PR battle, even if it didn't always win the battle in the skies. So for much of the war, while we were guarding the Norden with pistols and swearing bombardiers to secrecy, the Germans had the plans sitting in a file cabinet. They had already reverse-engineered it, tested it, and decided no thank you. The Brits, meanwhile, had a completely different philosophy, born of bitter experience. The Royal Air Force had tried daylight precision bombing in 1939 and 1940. Their bombers, the Wellingtons, the Whitleys, were slow, lightly armed, and they were, to put it bluntly, massacred. They were shot out of the sky in horrific numbers. So their leader, Air Marshal Arthur Bomber Harris, made a fateful and controversial decision. The RAF would abandon daylight precision bombing entirely. They would fly at night. And they wouldn't aim for a single factory. They would aim for the city that contained the factories. This was the birth of area bombing or carpet bombing. And for this kind of work, you did not need a $500,000 top-secret Norden. You just needed to find the city. The British developed the Mark 14. It was a simple, non-stabilized vector sight. The bombardier would dial in the wind, altitude, and speed, and the sight, which was just a system of cursors and a timing mechanism, would simply show him the correct aiming angle. It was cheap to produce by the thousands, it was reliable, and for the job of hitting a target the size of Berlin in the dark, it was all they needed. This isn't to say the British couldn't do precision. They had their own gyro-stabilized sight, the SABS, or Stabilized Automatic Bomb Sight. It was incredibly accurate, some say even more so than the Norden, but it was also incredibly complex and slow to use. So who used it? The specialists, the elite.
the 617 Dambreaker Squadron. When they performed their legendary bouncing bomb runs on the German dams, they used the SABS. The British had precision, they just saved it for special occasions. For the nightly grind, the simple Mark 14 was the tool for the job.
As the war dragged on, month after bloody month, that cloud cover over Germany remained the #1 enemy. The Norden, the Lotfа 7, the Sperry, all of them were useless against a solid bank of clouds. The real technological leap that truly changed the air war wasn't a bombsight at all. It was radar. Specifically, it was the H-2S, or as the Americans called our version, the H-2X Mickey set. This was a ground-scanning radar, usually placed in the belly of a lead bomber that could see through the clouds. It was a marvel. It couldn't see a single factory. The image was far too crude for that. But it could see the outline of a city. It could see the shape of a river bending, or the dark patch of a large industrial area, or the coastline. And this changed everything. The Mickey operator in the lead plane of a massive formation would guide the entire strike force to the target. He would watch his fuzzy, green glowing screen, and when his radar image showed they were over the aiming point, he would release his bombs. Everyone else in the formation, hundreds of planes, would simply drop their bombs when they saw the lead plane's bombs fall. This method was called bombing on the leader. And this is how the vast majority of American bombing was actually done from late 1943 onward. The prized, top-secret Norden, the Pickle barrel winner, sat unused in the nose, covered by its canvas shroud, while a radar operator in the radio room guided the strike. It's these kinds of technical details, the ones that get lost in the Hollywood versions of the story, that really tell the true story of the war. If you find this level of detail as fascinating as I do, I hope you'll consider sharing this video with a friend, or perhaps in a history group you're a part of. It's the best way to help others find this kind of in-depth information. But there is one more piece to this entire story. We've talked about gyroscopes and computers and radar and strategy, but what about the men? What about the bombardiers themselves? These were young men, many just 19 or 20 years old. They were pulled from civilian life, given a crash course in trigonometry, ballistics, and meteorology. Then they were handed the most secret device in the U.S. arsenal and told, in no uncertain terms, that the outcome of the war depended on them. They were trained to believe in the pickle barrel myth just as much as the public was. They were told that their job was to destroy the target and nothing else mattered. Then they were put in the nose of a B-17. They had to lie on their stomachs, eyes pressed to that rubber eyepiece, in a freezing, unpressurized aluminum tube, getting pounded by turbulence and flak, with enemy fighters ripping through their formation. They had to hold their hand perfectly steady, delicately turning to knobs, while their friends in the planes next to them were exploding in midair. The Norden demanded a calm, steady hand and a cold mathematical mind in the middle of absolute hell. The psychological pressure on these young men was immense, almost unimaginable. Many of those bombardiers after the war admitted the truth. The pickle barrel was a myth they had to discard on their first or second mission. Their real job, they learned, wasn't precision in the way we think of it. Their real job was to get the formation to the target and get everyone to drop their bombs in the same place at the same time. As we mentioned, the lead bombardier of the entire wing, or combat box, did the hard work. He was the most experienced, the steadiest hand. He was the one who actually used the Norden, or later the H-2X radar, to find the aiming point. What about the other 50 or 100 bombardiers in the formation behind him? They just watched the lead plane. When they saw his bomb bay doors open and his bombs began to fall, they toggled their own switches. They were dropping on the leader. This was the only way to get enough tonnage, enough high explosives onto a target to guarantee its destruction. The Norden's true value, therefore, wasn't as a precision instrument in 500 different planes. It was as a formation aiming instrument, used by the 50 most skilled men in the entire 8th Air Force. The rest were, in this sense, just along for the ride, carrying the payload. Now, what about the German bombardier?
His experience was different. His job was in some ways more collaborative. He often sat up front, right next to the pilot in the glass greenhouse nose of a Henkel 111 or a Junkers 88. He was in constant verbal communication with his pilot. Lefts, a little left, steady, wind is changing, hold this, hold, now. He was a true integrated crew member. The American bombardier, isolated in the nose, flying the plane by remote control, was separate, almost detached. The German system, many crews felt, was more intuitive. It allowed the pilot and bombardier to work together as a single team to solve the problem of hitting the target, while also solving the more immediate problem of surviving the mission. It's that human factor, that different way of thinking about a flight crew, that was just as important as the design of the gyroscopes.
So what was the final fate of these two competing technologies? What happened to the Norden and the Luftwaffe 7? The German Luftwaffe 7 was so effective, so reliable, and so brilliant in its fundamental design that it had a long and healthy life after the war. The Soviet Union captured the Carl Zeiss factory in Jena. They captured the engineers and the blueprints, and they used the Luftwaffe 7 design as the direct basis for their own post-war bomb sites for decades. It was a triumph of practical, robust engineering. And the Norden? Its story is, like the machine itself, more complicated. The sight as a physical object was a dead end. The entire idea of a visual mechanical bomb sight was obsolete by 1945. The future was radar. The future was electronics. And soon, the future would be guided missiles. The Norden was, by 1946, a museum piece. But the technology inside it, that's a different story. The gyros, the advanced autopilot systems, the principles of mechanical computing, all of that became the foundation for the next 50 years of aerospace technology. The Norden's a failure as a bomb sight, but it was a stunning, unqualified success as a technological stepping stone. It taught an entire generation of American engineers how to build the complex guidance systems that would one day guide our airliners, our first ICBMs, and even the Apollo spacecraft to the moon. So, we return one last time to that title. Why Germans scoffed at American bomb sites sans gyro stabilizers. We now know the title was, in itself, a riddle. The premise was wrong, but the sentiment, the scoff, was absolutely right. The Americans had gyros. In fact, our site was all about the gyros. The Germans scoffed not at a lack of stabilization, but at our method of it. They scoffed at the absurd complexity. They scoffed at the fragility, the need to baby this delicate instrument in a heated vault. But most of all, they scoffed at the doctrine, the suicidal idea that a pilot should hand over control of his plane to a machine and fly straight and level into a wall of flak and fighters. They scoffed because they had our plans, they had tested our secret, and they had, in their cold engineering opinion, already built something better. They scoffed, in short, because they saw the Norden not as a war-winning marvel, but a deeply flawed masterpiece, a beautiful, brilliant piece of laboratory engineering that just wasn't built for the brutal, ugly street fight of the war it was meant to fight. In the end, neither site truly delivered on that pre-war promise of surgical precision bombing. The technology in 1940 just wasn't there. The physics problem was too great, the weather too unpredictable, and the human element too fragile under fire. The air war was not won by pickle barrels. It was won by overwhelming industrial might. It was won by thousands of planes dropping tens of thousands of bombs, guided not by magic crosshairs in a visual sight, but by the crude, fuzzy green glow of a radar screen. The real story, as we so often find, is always more complex, more human, and more fascinating than the legend. We read your comments, and many of our best video ideas, like this one, come from the very specific questions you ask. If there's a piece of history, a technical mystery, or a what-if from this era that you'd like to see us tackle,
please let us know down below. We do our best to read them all. We covered a lot of technical ground today, from the specifics of gyroscopes to the harsh realities of radar bombing. If you enjoyed this, you will almost certainly enjoy our other deep dive on the P-51 Mustang's laminar flow wing and the design secrets that made it the best fighter of the war. And for those who preferred to listen while driving or working in the shop, we can also let us know in the comment box. Thank you for joining us today and for spending your time here.